Hello, everyone. I'm Kian, dev at Parity. We are very short in time, and I have a lot of stuff to discuss. Hopefully, I'll be able to fit them in 30 minutes, so I'll get right into it. I put one link in the message box. It's a YouTube link from Joshi's seminar. He talked earlier today, and he mentioned the seminar. I discussed almost the same presentation a few weeks ago in his seminar, and that's a link because we might want to skip some stuff today, or we might not be able to talk about all of them. So that's the full talk. Okay, let's get to Phragmen and NPoS problem. I'll first talk about sequential Phragmen, which is the basic of our election algorithm in staking and substrate. Then off-chain Phragmen, which was mentioned shortly today earlier by Tomek and his team as well. And maybe a short reference to offline Phragmen, which is a tool which you can use to play with all of this and do a bit more hacking with them. What I will not talk about, how Phragmen works in detail. It's very complicated. It's a big paper, and we have our own version on top of it. It's way beyond what I can fit in 30 minutes. Yeah, so our implementation differs a little bit. And so we use our tokens to indicate the weight of our votes and everything. We have some optimizations on top of Phragmen to make it better. And I would also not talk about that and how off-chain workers work. But luckily, we had a very good talk earlier today about Tomek and the rest of his team earlier today. So hopefully that's not really needed. But yeah, and anything which remains, we can take it to Discord, and I'll try and keep an eye on the message box as well. But yeah, let's see how it goes. So sequential Phragmen, a page in the history book of Substrate. About a year ago, we had this issue to change the staking election from a very simple, I think, token-based voting at the time to Phragmen, and this was introduced at the time, although at the time we didn't really have a chain. It was just back in the good old days of Alexander testnet, those of you who might remember. And so, yeah, let's see what Phragmen does in the simplest form. We have a bunch of nominators, which, I mean, someone also asked here, is it same as DPoS, delegated proof of stake? Kinda. I mean, I'm not the best with these terminologies, so I'm not going to say it. I'm not sure. But we have two entities, nominators who vote and validators who, well, you know who validators are. And here we have, we have 5 nominators, and each of them have a associated number of tokens. So N1 up to N5, and the number of tokens that they have. And they each put some votes, and by their votes, they only say who they are approving. So nominator 1 says, I'm approving validator number 1. Nominator 2 says, I'm approving these 2, and so on and so forth. So we have 5 nominators, 4 validators, and we want to elect 3 of them. So what does Phragmen tell us? Phragmen tells us first who is the winner. So first, this validator number 3 turns out to be a winner. Then, so it also works in rounds. The first V3 is a winner, then validator number 4, and then validator number 3. So we have now all the winners that we want. You can also see roughly based on the number of tokens that each of these have and the votes that they're delegating that these 3 are actually more desirable. But we're going to talk about that in way more detail down the road. And more importantly, Phragmen tells us the distribution of nominator stake among the validators who got elected. So in this case, nominator 2 has 20 tokens, but the question is, how do we distribute that between validator 2 and validator 3? In this case, Phragmen, this is actually a real example. You can run it in the SP Phragmen crate and you get the same result. Tells us to give 68% of the tokens of nominator number 2 to this guy. I'm having to read the chat box. It looks okay. And 32% to this guy, and continues. So for each of the nominators who had at least one validator who was among the winners, we have this sort of distribution. So now, knowing this, we calculate the final backing stake of the validator, which you can see, for example, for Kusama and Polkadot.js apps for each validator, which is the total amount of tokens that are backing each of these guys. So validator 2 in this case gets 36% of this 15 and gets 68% of this 20, you should follow my mouse cursor here, and it has a total stake of 19 backing this validator. And we can compute the same for all other 3 as well. And we call this backing stake or support in code. So we can have a quick peek at the code or the API of Phragmen as well. I'm not going to go into any details, just want to point out a few things because we'll be working with them later on in the talk. We have the struct called Phragmen result, and it has 2 fields, winners, which is a flat vector of just assume account IDs, which is just who is the winner. And we have another field called assignments, which is a vector of another struct called assignment. And each assignment is basically has 2 fields. I hope you can see that bottom corner. It has 2 fields. First, the nominator's account ID, and another. Yeah, I'm not sure if you can see that down there. Yeah, I hope you can see this. And distribution, which is a vector of validators, and the weight, which is assigned to each validator. We'll see this later on, but just to give you a overview of the code API of Phragmen. And this is implemented, it's part of the substrate primitive creates SP Phragmen. And well, you might ask, what is all the deal with this about? Let's talk alternatively. If I wanted to solve the same question, well, I would have seen the same graph. I would have said, okay, these 3 validators have more votes roughly, so I'll elect these 3. And for weight distribution, I would probably just say, okay, 50% is good here, and this guy voted for only 1 winner, so we're just going to give it 100%. And this guy as well, 50%. And we calculate the same stuff down there. And you might say, well, this is also okay. And this is probably how I would have solved this problem. And this brings us to the end, what we call, and you can also find this term in the Web3 Foundation research website or other contexts as well, the NPoS problem, the problem of how we should elect the winners and how we should distribute the stake between them. And Phragmen, as you see, is merely one of the potentially many solvers that can solve this problem. I also just introduced a very bad solver, but it still solved the same problem, which divided all the stakes equally. And some people who are way smarter than I am have proven that this to be a NP hard problem. It's an optimization problem. You can be stuck, like you're basically trying to optimize a few parameters. So the question is, what makes a good NPoS solution? And well, I mean, this could depend on the use case, but we want to have a secure chain most of the time, and more specifically for Polkadot and Kusama. So we define, or we can talk in the context of few parameters. Maximize the minimum elected validator stake. So among all the winners, there's going to be this one validator who's the cheapest one, or is the least back one. And if we maximize this, we alleviate a lot of risks. So the chance of, or basically in this context, when we talk about the attacks or the risks over the chain, we always, it's very important because the least backed validator is the most likely one somehow to misbehave because it has the least number of tokens and stakes. So if we maximize this, we are increasing the security of the whole chain in total. And maximize the sum of all stakes. So we want to have as many tokens as possible bonded in our staking system. And minimize the variance of all the elected validator stakes to have the least amount of variability among them. So the difference between the most backed validator and the least backed validator is somehow minimized. So you would have a more fair system. As mentioned, this stuff is it's very, very much in the depth of the research. I'm just the person who implemented them. We can chat about them more later in this course, but for now I hope you agree with me that these are good indicators of roughly a good NPoS solution. And now, interestingly, let's compare my solution, which gave us the minimum stake of 17.5, if you remember the graphs. And the sum of total number of tokens at stake was 75. And the variance, I mean, it's the square of this number that you have here, but I mean, we're just going to assume it's the sum squared of all the stakes, these three numbers. And the fragment that I showed at the beginning gave 19, which is, well, we can see it's better. It gave the same sum of stake, and it actually gave a lower variance. So maybe we can, I can go quickly back to them. Yeah, you can see that, for example, this was my solution, which divided everything 50%, 50%. And you can see now why Phragmen did this differently, because this guy is being back too little, 17.5, while this guy is being back too much. And Phragmen is essentially trying to alleviate this little by little. Okay. So this is, in the briefest possible way, how we're using Phragmen in staking. There's a little bit more. We also introduced, or we started using at some point, Phragmen for council election as well. Another page in the history of Substrate. And there are some minor differences, but roughly we ask Phragmen again to elect all the councillors for us. We elect 20 basically members with Phragmen, and we divide them into two chunks, 13 members and 17 runner-ups. And this is how we elect the council currently in Kusama. And Phragmen works in a iterative manner, as I mentioned. So we respect the order in which Phragmen chooses these members. So we say the first 13 are the best ones, so those are the councillors, and the next 7 are the reserved ones. And there's a minor difference. In staking, we always inject a self-vote which means that each validator automatically nominates themselves. In council, we don't. If you want to go for council, just keep that in mind. And one minor note that Phragmen is an unranked election at the end of the day. So we do take the first 13, but it doesn't necessarily mean that the first one is the most backed one, because at each step, Phragmen is adding one member to the list, and it doesn't really know who the next one would be. So sometimes the first one, which is elected, doesn't end up being the most backed one. And this is why in current Kusama Council, if you see, we have a different prime member election, which should be the most backed member. And it's a different algorithm, but outside of the scope of this talk. So again, moving along. And now off-chain Phragmen. How did it all start? About a year after the initial implementation in Kusama, we started noticing some blocks taking a lot of time at the end of sessions, and most notably at the end of eras. And two suspects were initially or immediately introduced: payouts, and now we have a different sort of payout mechanism. It's happening lazy, and it's evolving over time. And Phragmen. Both of these operations happen at the end of the era, and both take a whole lot of time. And we did some benchmarks, and it turned out Phragmen is also taking a lot of time next to payouts. So we decided to move it to the off-chain Phragmen method that we actually talked about for a long time, but the implementation was postponed for many reasons. And we also I mentioned that we have some optimizations on top of Phragmen to even distribute everything more. That's called the equalize method. And we also removed that to speed things up temporarily. And how the off-chain model works of Phragmen and how does it improve everything. This was also briefly mentioned earlier today, again, in the off-chain worker talk. We have the entire era, which is divided into a number of sessions. And the way that the off-chain Phragmen works is a certain number of blocks before the end of the era, something happens, like an event is triggered. It's not really a substrate event, but let's assume like a flag is raised, and we call that the opening of the election window. And during the election window, we have two dispatchable calls that can be used to submit a solution to this Phragmen, to this NPoS problem that I just explained. So the chain basically delegates the submission of the solution to the outside world. So everyone can submit a solution now back to the chain during this election window. And when the era ends, we look at the chain state, and if we have received any good solution, we always keep the best solution as we receive them. And at the end of the era, we look at the chain state. If we have a a solution queued and ready to be used, we use that. If not, we fall back to the on-chain fragment, which is what we were doing 2 days ago, basically. Yesterday, Kusama updated to this mechanism, and now it's actually working. So good timing, kind of. Yeah, so during this, again, to recap, during the selection window, different entities, both signed and unsigned, I'll talk about both of them, can submit solutions. And at the end of the election window, we have a fallback mechanism. If we have received a good solution, we use it. If not, we fall back to the previous method. And the submission of solutions has two variants, signed and unsigned. Signed means that any user, me, you, anyone can submit a solution, a transaction, and claim and hand in a solution. There's a long verification process that I'll talk about. Even more important is, and the reason that we call this off-chain fragment is because all of our validators run the off-chain worker code by default. This is the sort of the setting of how Substrate works. You can disable it if you want, but --validate implies you also run off-chain worker. And what we do is the validators, or we put this off-chain worker code, so validators compute the fragment, sequential fragment with a number of equalize, with this equalize optimization as well, off-chain, and then they submit it back to the chain. Exactly the scenario that was explained earlier today as a very typical off-chain worker use case. So an off-chain worker does a heavy computation, which is all that fragment weight measuring stuff, and then it submits the solution back to the chain as a on-sign transaction. And we actually also use that the source attributes of transactions that was explained just today and also recently introduced into Substrate, particularly for this use case. So the unsigned variant can only be submitted by a local node. We'll get to that later. So I hope this page and this graph talks or depicts the overall workflow of off-chain fragment. Yeah, so if the solution exists on chain, we use it, else we fall back to sequential fragment on chain. So yeah, an on-signed solution will only be accepted if it's generated locally, which means that a validator would, all validators run the off-chain worker code, and whenever it's their turn to author a block, they have a shot at submitting or including this solution into the block that they're authoring. So let's. I want to walk through these are the two dispatchable calls that you can use, or they're now in part of the substrate for off-chain workers. I want to walk and in each parameter and explain some of the details here. So you have submit election solution, the normal variant, and submit election solution unsigned, which is the one which is used by validators. First parameter, origin, nothing particular about it. One of them does ensure signed, one of them does ensure none. If you do any substrate development, you are definitely familiar with them. Yeah, nothing interesting. Then we have winners, which is a vector of validator index. You can assume, well, this is probably that flat list of winners that I talked about. But the thing is, as you see, I'm mentioning validator index, not ID. And you might ask, well, where's this index coming from? And the thing is, validators are stored in maps in storage. I mean, like a month ago, it was linked map, but we put that aside and it's now deprecated. It's still kind of a map, and enumerating it all the time is expensive. There's also the size overhead to it. So what we do instead is during the election window, staking is kind of locked. So you cannot really submit any extrinsics to, no, you can bond a new account, but you cannot unbond. You cannot change your nomination. You cannot basically change anything that might affect the outcome of a fragment solution. And this has a very good reason. But as the outcome, we can dump all the validators and all the nominators into flat lists or vectors and put them in storage. And now we can reference them by index. And this has a consequence for end users as well. So as mentioned, some operations of staking will be limited in this short period of time, usually like the last, 20 blocks of the last session, which we call the election window. And let's see why. So yeah, the validator index, let's see. I think this slide got, yeah, this slide is misplaced. And let's see the reason of why we do that. Let's look through an example. Polkadot or any other chain is live. We have 1,000 validators, and each of them is backed by roughly 200 nominators. And everything's great until you realize not at all, because with this numbers that I showed, and assuming that you don't submit indexes and you want to submit account IDs for validators and nominators in the Phragmen solution, a naive solution, if it's of a, okay, so now I have to talk about the degrees. If a solution is of degree 1, meaning that each nominator is backing only one validator, then we need 200,000 nominators. And if you multiply that, 200,000 nominator IDs, and each of them has a nominator ID and has to tell which validator this nominator is backing, plus the weight, which is the absolute, the total absolute stake, which is associated with that weight, with that edge. And assuming that we have addresses 32 bytes and we have stakes which are U128, this ends up having this size in number of bytes, which is almost 15 megabytes of data. And this is quite bad. And if you relax it a bit, so you have degree 8, which means that each nominator backs 8 validators, that's still, if you do the math and trust that I've done it right, I hope I have done it right, you still get pretty bad numbers. So this cannot work. And this is most notably why we do that indexing. So no addresses are used, we only use indexes. More importantly, we never submit the stake as a balanced number, as a U128, U64 or anything. Balances are submitted as a type which is per U16, which is like a ratio between, a ratio encoded as a U16. So basically it's 0 means 0. If it's U16 max value, it means it's 1. So we actually submit them as like percentages. And we use a compact type, which has some nice features, which is the next parameter that we're going to talk about. So after the winners, we have the compact assignments. Okay, this is like the piece of code which was kind of distorted before. If you want to encode this distribution, we have this assignment struct, which has a who field, which is the identifier of the nominator, and 2 in this case, and distribution, which is a vector of account IDs and a weight. So in this case, it would be v2 tupled with 50%, v3 tupled with 50% again. So, and this is pretty clean, and we replace it with this very nasty, ugly struct, which is very different, but it has some nice features that allow us to optimize a lot. And yeah, for the sake of time, I think I'm not going to go into lots of details of this, but I'm just going to tell which things it does better. With this struct, we never encode the length of any int vector. Some vectors are here removed by some fixed size arrays, and this is more optimized for encoding. And yeah, we also generate this struct with a macro. So if we happen to, and at the moment, this is important. At the moment, we can have, each nominator can have only at most 16 votes. So we need only votes 1 until vote 16. And if we have more, we can change the struct later on. And we also drop weights as much as possible. So as I mentioned, weights are now percentages. So if you have like if I vote for 3 validators and the first 2 weights are 25% and 25% respectively, we know that the third one is 50% because that's the rationale behind it. So we also drop the last weight of each distribution edge. And yeah, as mentioned, we also use U16, which is 2 bytes for weights, and as the indexes as well. The index of validators can be at most U16, which means yeah, there's like a limitation at the moment for the number of validators that can exist, but we are way that's way in the future until we hit that limit. And nominators can be U32, which is a lot bigger. So yeah, now let's do the same calculation, but for a compact solution. So we have again 200,000 nominators, and each of them now instead of the account ID, we have to encode the nominator index, which is 4 bytes, as mentioned, and a validator index, and which is 2 bytes. And as I mentioned, if each nominator is only voting for one validator, we don't encode the weight. It's obvious. It's 100% of their stake. And the number is way better. It's 1.1 megabyte. And yeah. And if we have the degree 8, we again have so 25,000 nominators. Each of them would have a nominator index, 7 entries, which is a tuple of a validator and a particular weight, and the last validator, I named it here target, which we don't even have to name the weight for because it's obvious. It's whatever is remaining. And in this case, we would have even less data. So this is like a snapshot that I took from a tool which I might have time to talk about later today, this morning, from the live Kusama network. And the normal assignment size without any optimization is around 117 kilobytes. Yeah, 117 roughly kilobytes. Whereas the compact assignment I just talked about with all these complications is around 4 kilobytes. So you can see the difference is huge. Although there's more. Now this is an example that I will talk about. It's the same fragment solution that I talked about, and I said supposedly I will solve it. And the only thing that I'm going to do is I'm going to replace the percentages with absolute values. No other difference. And turns out you can even optimize more, and this also contributes a lot to reducing that size. So this shape, I'm just going to sort of change the locations, but all the edges will stay the same. So this guy didn't really vote for anyone who's a winner. We don't talk about it. The other ones, I just distributed them in the page differently to depict the fact that we have a cycle in the graph. You can see these 5 entities are forming a cycle in this graph. And if we have a cycle like this, it turns out that we can always remove the minimum edge of the cycle without changing any semantics of the validator's backing stake. So what we do is we assume this 7.5 is the minimum, and we replace that with 0. And we now have to compensate this. So this guy had 15 tokens. These 7.5 have been vanished now, so we have to increase it to this edge. So we do that. And now this guy is getting a 7.5 out of nowhere, so we have to decrease this by 7.5. So we can see where I'm going with this. And if we do this all the way along, we end up with what we call the reduced algorithm. It's an optimization that we came up with. And the good thing about it is the total backing stake of all validators do not change at all. It's the same thing, only the edges change, and the validators would still end up having the same total backing stake. So all the 3 parameters that I talked about, like the qualities of the network, the 3 indications of a good NPoS solution, they don't change at all if we do this reduce. Yeah, so we don't change any of the criteria. Of course, this does tweak how a nominator's stake is distributed, but that's something that Phragmen is doing anyhow. And yeah, I'm gonna briefly talk about score as well. Hopefully I can finish in a few more minutes, or should I finish now, Caroline? Or I see that your face popped up, so maybe
I'll give you 2 more minutes.
2 more. That's
okay.
good. That's already okay. So last thing that we have in the solution is score, and I'm not even going to go on the slides. I think it will be distracting. How it works is we offload this computation off-chain, but we still have to verify it on-chain because we allow also, we allow validators to submit a solution. I mean, they do it by default, kind of. We also allow anyone to submit a signed transaction, and we know that anyone can And the point is that verifying this solution is also rather expensive, and we have to optimize it. And a really good way to do that is to ask anyone who submits to claim a score. And so what they submit in this score field is the 3 parameters I already talked about the quality of an NPoS solution. And what we do is we assume that the score is valid. So we assume that the score is good. And the first thing that we do is we check with any previously submitted solution and see if this score is actually an improvement. And if it's not, we early reject it. And this kind of depicts how we generally verify the solutions, both on signed and unsigned. And it's basically, we want to reject as many solutions as early as possible with the least amount of work. And this score submission is also part of that. So we assume that the score is legit, and then we do a bunch of other cheap checks, which are really easy to do. And then at the end, we check if the score is also correct. So we know that anyone can lie with their score, but we check it at the end of the day. We check it at the very end. So long story short, each score must also claim a score. And if it's not a good score, like even if your claimed score is not good enough, there's no point in continuing. I mean, you can have a very good solution, but somehow miscalculate your score, but then that's your problem. You lose your slot. So that's all in all, I think, how off-chain Phragmen works. It's, yeah. I think I walked into some stuff very quickly. I even confused myself at some point. If there are any questions, let's go to Discord, and I'll be there to answer questions. And thank you for listening. Yeah, that.